Hello everyone, in this lecture we're going to discuss radial basis functions. This is one of algorithms used in machine learning. The main idea is that we would like to separate non-linearly separable problems such as the XOR gate. As we know, the XOR gate, if we take a look at it, it has 4 points. We have 0, 0, which is this point. This is 0, 0, and we have, of course, 1, 1, and then we have 0, 0, 1, and we have 1, 0. And as we know, these two belong to a class and these two belong to another class. So typically we cannot have a line that is separating those two. So XOR has the characteristics of being non-linearly separable. So what we're trying to do here is we would like to solve it. And the way radial basis function does it is by a hybrid method. Okay, so RBF uses a hybrid method to achieve this. This hybrid method has two stages. So the first stage is actually given a set of non-linearly separable patterns, we want to go to a higher dimension where it is highly separable. So starting with non-linearly separable input patterns, transform it to a space where it is highly separable. And the second stage, what we're trying to do is solve it. Once it's linear, we can solve it using classical approaches for classification problems. So we can use in this lecture we're going to use least square estimation. Remember, here it is linear and here it is non-linear. So RBF relies on these two stages. And what do we mean by hybrid method? By hybrid, we will have the following structure. So hybrid methods. Of RBF. So it implies the following. We have an input layer, okay, and made of many neurons. We have a hidden layer, like classical multi-layer perceptrons. This hidden layer applies transformation from the input space to the hidden space or the feature space. So this applies a transformation from hidden space from input space to hidden or feature space. This is of course a non-linear transformation. Okay. Of course, the dimensionality of the hidden layer is 1. So we have many neurons in the hidden layer. However, we only have one layer, which is appropriate for most application. Okay, and third we have the output layer, so here we have going from, this is nonlinear, and here we went to be linear, and here we apply a supervised method for training. Of course, in this here we have unsupervised methods employed. Okay, so the hybrid method is we have unsupervised method for the transformation from the non-linear to the linear. Once we are at the linear stage, we can apply the supervised methods for training. So what RBF does is very simple. RBF takes a complex pattern classification problem and transform it into a higher dimension where it is linearly separable. So it takes a problem, it's a classification problem, transform it to a higher dimension where it is separable. Of course, here we are at the stage where it is non-linearly separable. And this is what's covered by what's known as Cover's theorem. And in this theorem, it says a complex pattern classification problem cast in a high dimension space, which is non-linear, is mostly likely to be linear in the higher dimension. So if you are at the 2D, it's and the problem is non-linear. If we go to 3D or 4D, probably it will be more likely to be separable. So of course there are some constraints and some points that needs to be covered before going into an actual implementation. So let's start with the derivation of this method. So first, let H be denote a set of n patterns that we would like to classify, vectors of x1 to xn, and each assigned to either h1 or h2. So in this case we have a binary partition or a dichotomy where we have a separation, where there is a separating space, separating a hyperplane that divides those two patterns together. So for each pattern, so this is a dichotomy. Or binary partition. Alright, so we start for each pattern x belonging to H, we have made up a vector of real values. So there is a vector of real values, we're going to call it phi I of x, where I goes from 1 to m1. So m1 is the dimension of the hidden space or the phi functions, and we can say, okay, big phi of x is the collection of these phi 1, small phi 1, small phi 2 of x, all the way to phi m1 of x, since it's of a dimension m1. So let's say we have m1 is the dimension of phi, big phi, and m0, let's say m0 is the dimension of the input Okay, so phi I of x, this guy, plays the role of a hidden function, hidden layer function. And this function will actually transform me from the non-linear space to a linear space. So remember that we have many neurons in the hidden layer. So we have actually m1 of these hidden neurons. Each of them has a specific function, phi 1 of x till phi m1 of x. And so we can say that these hidden functions, which are phi I of x, where I goes from 1 to m1, is referred to as the feature space. So these are the features that is in my data. So we have 2D data in 2D space. When we go to 3D or 4D, we have like magnified the features in these input data. And if we can find a w, a weight, so if we can find a w such that wt phi, big phi of x, is greater than 0, then x belongs to h1, and wt of phi x smaller than 0, x belongs to h2, then we have achieved our dichotomy or our binary partition, and we achieved a place where we can linearly separate those two, the input into those two partitions. So this W is in fact a hyperplane that cuts the feature space into two dichotomies, which is H1 and H2. And this hyperplane is as follows. So let's take a small example. So let's say we have a, let's say 5 points. Let's say this is the first two, and this is another set of points. So they are linearly separable because we can draw a line, and this is a line separating those two. However, so this is called linear, and this is first order rational variety, and we're going to talk now about rational variety. Now, if we have something like this, and so now clearly we cannot have anything linear, so we can have now a spherical separation, and here we have something called spherical or second order rational variety. We can have also something like this. So here we have something like a quadratic function that's separating those two. So here we have quadratic with line constraint, which is a higher order rational variety. And in this case, the hyperplane in 1D is a line, in 2D is a squared function, in 3D is a cubic function. So as we increase the number of hidden layer, we are going to a different dimension where we can actually separate those easily. So this hyperplane, so let's say the hyperplane we are talking about, which are one of these depending on how our data is set, is defined by the below equation. Okay, we have Wt phi, big phi of x equals 0. Okay, and we can have the inverse image of this hyperplane by saying, okay, this, so the inverse image is what are the x's that satisfies this formula. Okay, so in order to discuss this hyperplane, we consider using linear combinations of R-wise product pattern vector coordinates. So let's write this. So in order to discuss more phi and w, let's consider okay an R-wise product of pattern vectors. These separating surfaces are called rth order rational variety. So the separating surfaces are called rth order rational variety. And these are the rth order rational variety. So that what we mean by rth order rational variety, they contain non-linear terms such as x1, x2 plus, for example, or another x1, x2, x3. So they have multiple dimensions. So now a rational variety of order r of dimension m0, so we have the rational variety of order r and dimension m0, the input space, is given by the following summation for 0 less than I1 less than I2 all the way to IR less than equal to M0 is actually a constant I1 A of I2 all the way to IR times xi1 xi2 all the way to xir, and this is equal to 0, where xi is the ith component of this vector. So this rth order product of entries of xi is called a monomial, and there are many combinations of monomials. So if you have a dimension of m0 and rth order, we can have the below, since it's a combination, the below different monomials. Okay, so these are different monomials. And one thing to note that if it's quadratic, if it's linear, then it's definitely separable in 2D space when we have spherical in second order, not 2D space, in second order, and also in the third order. So if it's linear, then of course it's separable in higher order. But if it's quadratic, it's not necessarily separable in spherical or in the linear phase. So if you go down, if you increase the dimension, then of course we have high probability of being separable. So what are the effects of dimension of M1? So increasing M1, so let's talk a little bit about effects of M1. So increasing M1 will actually increase the probability of having linear separable phi space. Increase probability of having linear separable phi space. However, this is not for free. It comes disadvantage, higher complexity. Now, separating a capacity of a surface, so if we have M0 and M1 in dimension, if we increase the number of inputs to be separable, then we have the following. So what is the maximum patterns that we can classify if M0 and M1 are fixed in dimension? If M0 and M1 are fixed, the maximum number of separable parameters is said to be 2M1. So where M1 is the dimension of the hidden space. So if we have 4 hidden neurons, then maximum we can have 8 separable patterns. So in this case, you can place an upper limit on the number of expected patterns that we have in our data. Now, to bring things closer, let's take the XOR example again. So with the XOR example, of course we have 4 points, 0, 0, 0, 1, 1, 1, and of course 1, 0. So we want to define a pair of hidden Gaussian functions. So let's say that the phi function is Gaussian. Of course we can have others, but for sake of simplicity, let's take these two. So we have phi 1 of x is equal e to the minus x minus t1. This is for phi 1 squared, and phi 2 of x is equal e to the Euclidean norm. Of course those two dashes is the Euclidean norm. This is for t1, the desired value, equal 1 comma 1, and t2 equal 0 comma 0. We chose those two because we want to draw it on a 2D space. Of course, in real life, we need to go to, we have phi 3 and we have phi 4, but we're not going to use them in this example. So in this case, M0 has, the dimension of the input is 2, and M1, we're just going to use 2 hidden neurons. So actually, we're not transforming it to a higher dimension, but we see it can do the trick. So x, t1 and t2, all of them have a higher dimension. So if we plot those values, t1 and x1, so we have something like this. Let's put a table. So of course we have x, the input pattern. The first pattern will be 1, 1, and then 0, 1. So these are the x's, 0, 0, and 1, 0. And this is the first hidden function is phi 1 of x and phi 2 of x. I have t1 and I have t2 and I have these values. So here we have 1 and the y1 because t1 equal 1, 1. So when we plot x as 1, 1, we have here, let's put it aside, e to the minus 1, 1, Euclidean norm, minus 1, 1, which is going to be 0. So e to the 0 is 1. Phi 2 will be 0.1353. For 0, 1 is going to be 0.3678, and we have also 0.3678. This will be 0.1353, and this is 1. This will be 0.3678, and this will be also 0.3678. So if we plot this in the phi space, so this is phi 1 and this is phi 2. Now we can see we have a point, 2 points here actually, 0, 1 and 1, 0. These two, they are at the same point at 0.36 and 0.36 or 37 if we round it up, and we have point here 0, 0, here, and we have 1, 1 here, and the second point is 0, 0. So now we can see that in the phi space we can linearly separate the input data. Previously, data that were unseparable in the input space, by transforming them into 2D space or the phi space, it was from 2D to 2D. So by transforming them into the phi space, they can be linearly separated. Okay, so how can we generalize this into a algorithm? So we start what's called the interpolation problem. So with the interpolation problem, we have an input layer, dimension equal M0, a single hidden layer, dimension equal M1, and the output layer, also the dimension. However, here the dimension is just one for simplicity. It can be more than one. So what we usually do with the radial basis functions or RBF technique is that we have the input here, the input dimension, and we go with a non-linear transformation to the hidden space, and then from the hidden space we go to the output in a linear fashion. So it can be looked as from input to output non-linear, and here we have our separation. So now for the interpolation problem, it can be looked as a mapping from space of dimension M0 to a space of dimension 1, since we have only one dimension at the output. So this needs to be passed by a hypersurface. So the hypersurface that will separate those is of dimension M0 plus 1, and I'm going to explain why. So the dimension of the hypersurface is M0 plus 1. So imagine we have 2D points, okay, and we can transform those 2D points into a 3D space where we have points all over, okay, and these are the projections on the XY plane where they were. And we can see here that if we want to go from R2 to R1, we can fit a surface which is a 3D surface that can encapsulate all these points. So the problem now is finding this surface. So this is why we go to a bigger dimension in order to fit a curve over this 3D space. Remember that the values of each of these points correspond as corresponding on the z-axis. So the output here will be the z-axis, which are the points here, and the problem will be finding this hypersurface. So in order to do this, we have a training phase and a generalization phase. So with the training phase, what we do is it's an optimization procedure for optimization of a fitting procedure. So what we do, what we mean by that is that there is known data points in the form of input-output examples, and we want to clean up outliers and noise for the fitting procedure. So this is what the training phase is. So we have the 3D model, and now we have those points here in the training phase. In the generalization phase, so let's say cleaning data from noise. Okay, in the generalization phase, we fit the curve. So now we have in the 3D model a curve that is encompassing all these points in 3D surface. So we interpolate between data points over a constrained surface. Once we have that surface, now we can plot any line and we get the output, which is on the z-axis in case of a 3D module. Okay, so constraints are in the form of given known data points that the surface should pass. So the constraints here are known data points the surface should pass through. And the output of the interpolation is the approximation of the true surface. So now, with the interpolation problem, we have a set of points, we take them to a higher dimension, we clean up the data and remove outliers, and then we fit a curve so that we can know the output. However, if you want to state the problem in a more RBF fashion, we can do as following. So the problem now can be stated as follows. So we have given n set of different points, dimension equal m0. So now we have xi belongs to Rm0, where I goes from 1 to all the way to n. Okay, and of course we have since this is supervised, we have the desired output. The output, remember, is just a single dimension. So E of I belonging to R, where R goes from where I goes from 1 to all the way to n. So the problem can be seen as a mapping function f that takes me from m0 to r1. Remember that we have input and output. So, however, it should satisfy the constraint f of xi is equal d of I, for I equal 1 to all the way to n. So using radial basis functions, f of x can be looked as summation as I equal 1 to n for wi phi, the norm of x minus xi, where this operator is the Euclidean norm. So this can be the Euclidean norm of x minus xi is actually equal to the square root of x minus xi times x minus xi. Okay, these are all vectors. So we note here that we have phi. So phi of x minus xi for I equal 1 to n is known as the radial basis function, and we're gonna discuss the options for these, and these are n arbitrary functions. So we're gonna specify those for arbitrary functions, and if we take like a matrix look at these, so remember that we have f of xi equal vi, so we have phi 1 1, these are the phi 1 2 all the way to phi 1 n, as we go to here to phi n 1 until phi n n, and multiplied by a weight matrix, they will equal to the desired values. So n patterns gives n different RBF functions centered at x of I. So we have f of x is equal to summation of, to recap, wi phi x minus xi, and we have phi ij is equal phi x minus xj for I j equal 1 all the way to n. Alright, so given this fact, we have an n by 1 representation of linear weight, and we have an n by n matrix of phi, which consists of all these phi's. So we can say, so let's say this is equal to big phi. So we can say that phi w is equal to d, implies w is equal phi minus 1 d, given that this should be non-singular, so that we can find an inverse, and this will be discussed next lecture, next slide. So now, what are the RBF function phi, which we don't know right now, that can be non-singular and fit for our example? So we have, so there is a large family of radial basis function covered by McKinley's theorem. So the main important that they should be non-singular. So we have RBF functions. We have one, the multi-quadratic. And where we have phi of r is equal r squared plus c squared half for c greater than 0 and r belonging to r, big R. We have the inverse multi-quadratic. And in this case we have phi r is equal to 1 over r squared plus c squared half, for also c greater than 0 and r belonging to big R. And the third is the Gaussian, which is phi of r is equal e to the minus r squared over 2 sigma squared for some sigma greater than 0 and r belonging to r. So for all the radius function discussed to be singular, the point xi must be all different distinct. So the main requirement here for use for any of these functions is that xi for I equal 1 to n must be distinct. So we need to clean our data from duplicates before applying any of these RBF functions. So now if you want to look at the formulation, we have the following. So here we have x1 to xm0, since we have m0, and then we have, this is the first hidden layer, first neuron in the hidden layer, phi 2 all the way to phi n. Okay, and then we have, this is the output layer. Remember, we have a single neuron. We have here W1, W2, and Wn. And of course, the axes are all connected. Okay. And of course, this is centered at x1. This is centered at xn. This is here the summation. So once we do the transformation from the input space to the phi space, given using the functions, remember here if we have n patterns, implies I need n neurons in the hidden layer. That's for the interpolation problem. So and the output neuron consists of just a single one. Remember that phi j of x is equal phi of x minus x j, which is exponential of 1 over 2 sigma squared j, sigma squared x minus x j squared for j equal 1 all the way to n. So each of these, if we use the Gaussian function, each of these hidden neurons is centered around x1, x2 till xn. So typically we have a common width of this Gaussian function centered around sigma. We don't have different sigmas for different functions. However, one thing is that having a solving this for the interpolation part, this is as an interpolation problem, we have some problems here. First is that interpolation solution can be confusing in this case. And in what sense is that it can lead to misleading results, because especially when we have high noise. So with high noise we have misleading result. Second, we have large number of input neurons. Suppose that you have 1000 training patterns. So shall I use 1000 hidden neurons? What about 10,000 and more? So the number of hidden neurons is very large, which may increase computations. So we need a different way to compute the number of hidden layers, especially that input patterns usually are close to each other, so there's no necessity for assigning each input pattern a Gaussian function centered around it. Maybe we can group those together and create a cluster for grouping all these inputs around a single Gaussian function, and this reduces the number of number of hidden neurons in the hidden space. So one method to do this is using Kmeans clustering. So what Kmeans does is just it clusters nodes around a thing, around an average. So what Kmeans does, as we said, so we have certain points. Let's say this is. So what Kmeans does is that it clusters data points and represent them with a mean or average that represents this cluster. So instead of saying, okay, I need for each point to be represented by a Gaussian function, now I can say, okay, no, I can get the mean, and this mean of this cluster have nodes, have points that belongs to it, and we need to represent it now by its mean instead of by its individual nodes. Okay, so let's say we have input data. We have xi, I goes from 1 to n, and we have a multidimensional observation, and we have m patterns. We need to represent them by k clusters, where k is less than n number of patterns. If you take a look at this example, we have around, let's say, 15 points. We can represent this, instead of having 15 points, we can represent them by 3 clusters. So, and remember, this is an unsupervised method, since we don't know the number of clusters, or we don't know which points is belonging to which cluster. We don't have a desired output, so we can call the clusters as C of j. Okay, and we want to find that j, the neuron j or the neuron I, belongs to C of j, where j is equal 1 to all the way to n. Now what we want to do is we want to minimize, we want to find those means or averages that represent each cluster. So now we want to minimize the cost function, where it's equal to summation I or j equal 1 to k, 1 from the number of clusters, for a cluster belonging to this neuron. We have xi minus uj squared, where uj is estimated mean of cluster j. So imagine this is cluster j, we estimate a mean, and what we're trying to do is minimize the cost function of all nodes belonging to this cluster. So to take a numerical example, let's show the following. Assume you have a two-dimensional data set, okay, and this two-dimensional data set and we want to have k equal 2, so we need 2 clusters only. So in this case we need to specify the number of clusters. It's very easy to specify if you know your data. So let's say you do character recognition and you have 3 different characters, or you have 25 different characters, so you choose clusters of 25. You don't have to use 1000 training patterns. We can only use just 25 for all the letters. So given the data sets 1, 1 and 1, 1, we have 2, 1, 4, 3 and 5, 4. So this is our data set. So we choose randomly. We can notice here that this belongs to one cluster and this belongs to another cluster, and we have k equal 2. So first let's use an estimated mu1 for cluster 1 to be the first point arbitrary, and mu2 to be 2, 1. Okay, so now what we need to do is we need to calculate the Euclidean distance between each point and the mean to find which point belong to which cluster. So with k-means, what I'm trying to do, I have a set of points, I have a number of clusters, and I chose 2 means from the points. Okay, these means will change. So I need to identify which points belongs to which cluster. So I can draw a nice table here, and I can say, okay, this is cluster 1, this is cluster 2, and these are the points. So if I try 1, 1, which is the first point, if I find the Euclidean distance, which is square root of x1 minus mu1 and the x2 minus mu2, well, it's not the mu2, it's actually mu x or mu y. Okay, then we can say, okay, we have 1 minus mu1, 1 squared, plus 1 minus 1 squared is going to be equal to 0. And if we try point number 2, which is 2, 1, we have here 1 minus 2 squared plus 1 minus 1 squared is equal to 1. So in this column we're gonna write j. So which cluster, we need to find the minimum distance. So of course, which cost is bigger? This cost is bigger, so we need to choose the minimum, which is the closest to this cluster. So I'm going to choose cluster 1. So now I try the second point. So again, I find it's equal to 1, and of course this will be equal to 0, and so this belongs to cluster 2. But wait, we said that these are very close to other, they should belong to the same cluster. Well, we need to wait until the algorithm finishes. So the third point is 4, 3. So we calculate this. 4 minus 1 squared plus 3 minus 1 squared is equal to 13. And we have 4 minus 2 squared plus 3 minus 1 squared, which is equal to 8. So now 8 and 13, this will win. And the last point is 5, 4. So you notice here I switched x and mu. It doesn't matter because it's squared. 5 minus 1 squared plus 4 minus 1 squared equal 25, and we have here 5 minus 2 squared plus 4 minus 1 squared, which will equal to 18, and this will be 2. Now we need to update the means and continue with the next iteration. So of course this point is the only one, so I'm gonna keep it the same. There's no change for the mean. However, for the second mean, it now has 3 points. So I need to take the average of these 3 points. So I take, since it's 2-dimensional, so we have 2 plus 4 plus 5 over 3, and we have 1 plus 3 plus 4 over 3, and this will be equal 11 over 3 or 8 over 3. So this is the new mean. Now for the second iteration, I do the same table again. And now I have, these are the points. I have C1, C2, and of course I have, so remember C1 here is still 1, 1, and C2 now is equal 11 over 3, comma, 8 over 3. So we have 0.11, and here of course we still have 1 minus 1 squared plus 1 minus 1 squared is equal to 0. And now we have 1 minus 11 over 3 squared plus 1 minus 8 over 3 squared, which is equal to 9.8. So I'm going to choose the minimum, which is 1. I have to 1. Of course, I will have here equal to 1, and this will be equal to 5.57. So I'm going to choose 1, and 4 over 3. And 5 over 3. So again we have 4 minus 1 squared plus 3 minus 1 squared is equal to 13, and here the new mean 4 minus 11 over 3 squared plus we have 3 minus 8 over 3 squared, and this will be equal 0.22. so I'm going to stay with 2, and here I'm not going to do it again. It's 25, and here is equal to 3.572. So we can see here that we have the separation done as we notice in our data set, and now mu1 needs to be updated because we added a new point. So now it's going to be the average of 1 plus 2 over 2, and I have 1 plus 1 over 2, and this will be equal to 3 over 2. This is the first cluster mean, and we have mu2, and it's going to be of course change incorporating 4 plus 5 over 2, and then 3 plus 4 over 2, which is going to be 9 over 2 and 7 over 2. So this means we have two clusters, one containing point 1 and 2, and another containing point 3 and point 4, and of course they have the two means mu1 and mu2. So we see here that Kmeans has, it's an algorithm that runs in iterations, and we keep on doing this until no weight change. So if you go, this is iteration 2 by the way. So if you go for iteration 3, we notice that no changes. So whenever we don't have any change, the algorithm stops. So if you do mu1 and mu2 with 3 over 2 and 1, 9 over 2, 7 over 2, and we did this table again, we still have 1, 1, 2, 2. So there's no changes in the mean, so nothing is changing. So if we continue on doing thousands of iterations, we're going to still have the same mean. So to reiterate, we have points, we have number of clusters that we need, we calculate the Euclidean distance between each point, so we can find the temporary means of these clusters. We continue on doing this until there's no changes in the cluster means, and we reached for two clusters. So remember here why we are doing K-means. We are doing K-means because we don't want to use n hidden layers, and we don't want to use n neurons in the hidden layers. We want, instead of using like here four neurons, we want to use, or how many, 4 points we have, we'll use only 2 hidden units instead of 4 hidden units, and this way we minimize the computation a lot. In order to find the weight update, we need to find that in a way it minimizes the difference between the input and the output. So remember that we used K-means to find the clusters. However, this was unsupervised. However, I have a given function f of xi equal di. So I need to find the weights that minimizes this function. And remember that the error previously, it was equal, the instantaneous error from 1 to n, and we want to minimize the distance between the weights, the output that we have from the hidden layer or from the previous layer, from the output layer. However, here we don't have xi, since we did a mapping to the phi space. So this becomes, so we don't have xi. Actually, we have an RBF minus wt and the big phi xi squared. So now we need to minimize the error. And the way we do this is we take, of course, the partial derivative with respect to w, and we will have this formula, which is r of n is equal or times the weights, minimize weights, times r of n for n equal 1 to all the way. So of course, this is multiplication. So of course, what's r of n? What's big R of n, small r of n? So we have r of n is equal to the summation from I equal 1 to n for phi of xi times phi t of xi. And remember, phi of xi is equal phi of xi. Now we have, of course, the new centers that we found using Kmeans, and then phi xi u2 all the way to phi xi. Remember, we have k clusters. Okay, and of course phi of xi mu j is equal e to the minus 1 over 2 sigma j squared xi minus xj squared. And of course we have r of n is equal to, which is a k by 1 cross correlation. This is a k by k correlation, r of n. So r of n is equal to summation I equal 1 to n phi big phi of xi times d of I. So now all we need to do, if you take a look at this formula, all we need to do is find Rn minus 1. So I'm going to write again. So we have this formula, Rn times Wn equals small r of n. So W of n is equal r minus 1 of n times r of n. So now the point is finding r minus 1 of n. Okay, and you can go over the mathematical formulations in the book or any book, but what we have is we're gonna solve it in a recursive matter, since Kmeans is also recursive. And we end up with having an intermediary step, which is Wn is equal, we would like to have this, the previous value, the current value depends on the previous value, minus 1 phi of n alpha n, where alpha n is equal d of n minus wt of n minus 1 phi of n. So we want to find r minus 1, So recursively, let's assume r minus 1 is equal p of n. For simplicity, we're gonna say p of n is equal p of n minus 1. This is the RLS algorithm, which is the recursive least square, minus pn minus 1 phi of n phi t of n pt of n minus 1 over 1 plus phi t of n p n minus 1 phi of n. And now we say that w of n is equal to w of n minus 1 plus, as we said before, r minus 1 phi of n alpha n, and we can say g of n is equal r minus 1 phi of n, and this will be equal to p of n phi of n, implies w of n is equal to w of n minus 1, just to make the formula a bit smaller, g of n alpha of n. This is n. Okay, so I just placed g of n instead of this formula. So to recap, first we have the points, then we find the means, and then we go with the RLS algorithm to do the weight update. So if I want to do a summary of this algorithm, so summary of RLS, so starting with phi of I, d of I, where I equal 1 to n, we do the following. We have p of n is equal p of n minus 1 plus the same formula, over 1 plus and g of n is equal to p of n times phi of n, and alpha of n is equal to d of n minus w t n minus 1 phi of n, and the weight update will be so after computing p of n and g of n, now we can calculate the weight update. We initialize the algorithm as following. We have w equal w at iteration 0 is equal 0, and we have p of 0, the first p matrix is equal lambda minus 1 times the identity matrix, where lambda is small and positive. Of course, lambda is used in the error function, in the average error function, the regularized parameter to when minimizing the error. So the effect of lambda is as following: lambda equals 0 means full confidence in the observed data. We have also lambda equal infinity means no confidence in observed data. So we typically choose a small value to indicate there is some sort of confidence in our training sample. Of course, for one thing to note is that we use the Kmeans to find the K clusters that we use to construct the hidden layer. so which has a dimension of m1 determined by the proposed number of cluster k. K may be viewed as a degree of freedom under the designer's choice. Of course, the cluster is computed by using unlabeled samples, and when we want to choose sigma for the phi function, we can use sigma as d max over square root of 2k. This sigma is used for the exponential function that we are using here. So remember, we need an exponential function, and sigma j can be used, I write it here, d max over square root of 2k. K is the number of clusters, d max is the maximum distance between any two clusters. So we find, if we have 5 clusters, we find the distance between each pair, and we choose the distance to be the maximum between them. And this finalizes this lecture. Next lecture I'm gonna do a numerical example on this topic.